Here is another take of the finite geometry video. So we should recall the three axioms. A1, there exists exactly 4 lines. A2, any 2 distinct lines have exactly 1 point on both of them. And A3, each point is on exactly 2 lines. And using these axioms, we're going to prove that this geometry has exactly 6 points and that each line in the geometry has exactly 3 points on it. So, because of A1, we know that there have to be 4 lines. We will call them A, B, C, and D. If we start with a point 1, we can determine that it is shared by lines A and B because of A3. So now we have 2 lines, A and B, that share 1 point 1. So we know that there has to be more than 4, or exactly 4 lines based on A1. So in order to create more lines, we need to create more points. So you can then draw 2 more points on line A, points 2 and 3. So that way additional lines can meet at these points based on A2 and A3. Now there are 2 lines, A and B, and 3 points. Returning to A2 and A3, the points need to be connected by lines. Using A1, because we have to have 4 lines, you can draw a third line, C, that has to, based on A2, connect to another point that is not being shared by 2 lines. Drawing line C off of point number 3, you can connect it to a new point 4. This new point 4 can be shared by lines B and C, based off of A2 and A3, because any 2 distinct lines have to have exactly 1 point on them, and each point is on exactly 2 lines. Point 2 is still not shared, which makes it incomplete based off the fact that each point is on exactly 2 lines and point number 2 is only on 1 line. So also because of A1, we still need 1 more lines because we only have lines A, B, and C. We need that 4th one, D. So we will add another point 5 and draw another line D to connect points 2 and 5. However, point 5 does not respect A3 as it is not on exactly 2 lines. Because of this, you have to add 1 more point. And to respect A1, we cannot just add a line because we have to have exactly 4 lines, but we can extend lines D and B to connect 6 to cover A2, which states any 2 distinct lines have exactly 1 point on them. And then you can extend line C to connect 5 for A3, that each point is on exactly 2 lines. So this is what I just talked through, starting with A and B on point 1, and then creating these 2 points, and then creating point C and connecting line C to line B with this point, and then creating 5 from 2, and then just extending the lines. So A is this blue line, B is the pink line, C is the purple line, and D is the green line. And we have to have only 6 points on this geometry, because if we were to add a point here, then we would have to extend more points, which by doing this, then you wouldn't have exactly each point on exactly 2 lines, A3, and any 2 distinct lines have exactly 1 point on them, A2. You would have to draw more lines, which would kind of X out A1, that there exists any 4 lines. So if we were to draw another point, we would have to break A1. And then as for proving that each line is on each point is on exactly 3 lines, we can see each of these lines, how there are 3 points on them. And really, you can't overlap the lines, because then you would have less than 3 points on them. And so you can see that we have this one that has 3, one has 3, or line B has 3, line A has 3, line C has 3, and line D has 3.